Right, so welcome everyone to today's Autonomy Talk. It's a great pleasure to have Yasser Shoukry with us today. Yasser is an associate professor in the Department of Electrical Engineering and Computer Science at the University of California, Irvine, where he leads the Resilient Cyber-Physical Systems Lab. Before joining UCI, he spent 2 years as an assistant professor at the University of Maryland, College Park, and he received his PhD in electrical engineering from the University of California, Los Angeles in 2015. Between September 2015 and July 2017, Yasser was a joint postdoctoral researcher at UC Berkeley, UCLA, and UPenn. His current research focuses on designing and implementing resilient AI and AI-enabled cyber-physical systems and IoT. Yasser's work has been recognized by many awards, such as, for instance, the Early Career Award from the IEEE Technical Committee on Cyber-Physical Systems in 2021, and the NSF Career Award in 2019, just to name a few. The title of today's talk will be Assured Perception and Control of Autonomous Systems Using Formal Verification of Neural Networks. And we're very happy to hear more about the topic and warmly welcome you, Yasser. The stage is yours.
Thank you a lot for inviting me and for the very nice introduction. So let's jump directly into the topic of today's talk. So we all know neural networks are everywhere right now in our autonomy stack. So they are used to implement a lot of different tasks and have enabled a lot of technologies and took us a step further towards this dream of having autonomous systems working up in the in open environments. Nevertheless, these neural networks are still not robust. They fail a lot in real life scenarios. So here is an example of a Tesla car doing the auto summon. This is like a perfect scenario where there is no occlusion, there is no no rain, no snow whatsoever. Yet the neural networks inside this system failed to take the right decisions and was about to hit the pedestrian. Similarly, on the video below, same story, the red car failed to stop correctly, which was going to lead into an accident out there. And everyone, and then we hear more and more of news of these neural networks failing in real-life scenarios, leading to some fatalities, crashes, and even some of the companies had to leave the market because of the lack of capabilities of neural networks to reason about real-life scenarios. So here at the bottom, this is the CEO of the Starsky Robotics, which is one of the first companies that was able to get legal permits to operate in California. And after raising billions of dollars, they had to go out of the market. And in this blog by the CEO, he was talking about the fact that machine learning, everyone had a lot of expectations about machine learning, that it will be able to solve a lot of problems, while in reality, it couldn't solve several problems. In particular, safety was a big concern of using these neural networks in safety critical systems. So the question that we are interested in is, someone is going to design a neural network that will do, for example, either perception or do control or whatsoever. And now we would like to certify that this neural network is correct. It can take the right decisions at right times for all possible scenarios. So how we can certify neural networks? Well, the first idea, maybe try to come up with theoretical proofs about their generalization. And there is a community in machine learning that is interested, that's trying to push the boundaries of coming up with better theoretical proofs about generalizability and so on. But we are still not there that we can certify the correctness of neural networks theoretically yet. The other way, which is what happens in the industry, which is just random testing. You have a data set, that you use part of it for training and use the other part for testing. And if you pass testing, then you say, okay, I'm happy with my neural network. And of course, we know based on the articles I just showed you that random testing is not enough to make sure that you covered all possible scenarios that the neural network will face in real life. And what we have been working on for the last 5 years or so is this use of automated reasoning and formal verification. So for those who have, for the students who have never heard about automated reasoning before, I highly suggest reading this particular article out here from Amazon Science about the use of automated reasoning. It is a subfield in computer science which is focused on exhaustive verification of complex software. Whenever you have a very complex system that you cannot reason about yourself, about its correctness and so on, automated reasoning can become handy out here, where it can look into your complex system and try to verify certain properties of your system and give you a machine constructed proof about the correctness of this system. So while there have been a lot of work on formal verification for software and hardware that become part of the industry, there is still not a lot of tools to do formal verification of neural networks. So around half of my talk today, I will try to establish some results and some tools about the formal verification of neural networks. Given a neural network that is already trained as some property, I would like to design this software that I will call the model checker that will take the neural network and the property and tell me, your neural network is perfect. It satisfies this property. There is no need for you to do testing. I will give you a proof that it is correct. Or I will tell you your neural network does not satisfy the property, and I will give you exactly what will go wrong with the neural network, what input that go to the neural network that will produce bad outputs. Then once we establish these kind of results and tools, I will briefly talk about how we can use these tools to develop assured perception, assured neural network perception. So the problem there is we would like to have a neural network-based estimator, and we would like to bound the errors that we will get from this neural network-based estimator when it is trying to detect certain objects of interest. And then I'll talk about how we can use, how we can design neural networks that we can use as a feedback controllers, again, with some kind of assurance in their capability of generalizing to unseen environments. So let me start with the first one, with the formal verification tools. This is work done by my PhD student Haitham and my postdoc James Ferles. And by the way, feel free to stop me anytime if you have any questions. So the first problem of analyzing neural networks is what's called as the input-output verification. So given a trained neural network, given an input set I will call Px, and I'm going to assume it is convex for now, and an output set Py, which is also assumed to be convex. The input-output verification problem asks for the following. Can we make sure that all inputs inside Px, when they propagate through the neural network, will produce outputs inside Py? In other words, a bad neural network is the one for which there exists one input inside Px, such that when it propagates through the neural network, will give you an output outside Py. That's a counterexample. If a counterexample does not exist, then this neural network satisfies this input-output specification. Formally, this is the set of all counterexamples. So this is the set of all inputs within Px that will generate outputs outside Py, and you can add some input-output constraints if you are interested or not. If this set is empty, this means this neural network satisfies this input-output specification. If the set is not empty, then this is the list of all counterexamples that will fail in this neural network. So what are these Px and Py? There is multiple different applications. You can use them to define what are these Px and Py. For example, we know neural networks are susceptible to what's called as adversarial inputs, which is a very small change in your images that will make the neural network get confused and give you different output compared to what was supposedly to be. So to check whether a neural network is robust or not, you need to check the emptiness of the set of counterexamples, which are all the images that are X that are close to the targeted image X prime, such that X minus X prime is within some epsilon ball. So these are all so X minus X prime is the error or the noise that you need to add to the signal, such that the neural network will provide an output that is not the right output that it was supposed to do. That's an example of how we can get with this PX and PY. Another example, maybe unrelated to autonomy, but still interesting, which is fairness. So you have neural networks that can be used to decide whether you can take a bank loan, for example. And you'd like to make sure that these neural networks are not going to discriminate based on some sensitive attribute. So to get this PX and PY, you take your neural network and you have 2 copies of them. You fix the sensitive attribute, one of the neural networks to be 0 and 1 for the other neural network. Now, this PX is going to be the set of all other attributes. And you'd like to make sure that the neural network is fair, which means it will always provide the same output regardless of the sensitive attribute. So you take the outputs of these 2 neural networks, subtract them, and you'd like to make sure the difference in the output is equal 0. So this means for all the inputs inside this PX, and regardless of the sensitive attribute, the neural network will take exactly the same decision. And the number of applications is growing every time. You can use the same exact methodology to construct PX and PY that can certify that a neural network is a Lyapunov control function, or it is a barrier certificate. If you have a controller, for example, that is going to guide air vehicles to make sure that they are not going to hit each other, and you'd like to ensure the correctness of this neural network, again, you can pose the same exact problem using this formula out there. So this is a general formula that encapsulates a lot of different problems underneath. The question is, now, given this some PX and PY that comes from one of those applications, how you can certify the correctness of the neural network, or how you can find a counterexample. So let me show you the most naive way of solving this problem, just to understand why the problem is hard. We know theoretically the problem is NP-complete, but just to give you a sense of where the combinatorial problem is coming from. So here is the simplest possible neural network with 2 ReLUs, with 2 neurons, Y1 and Y2. And here I'm assuming we are using the ReLU activation function as the nonlinearity of the neural network. This is the state-of-the-art activation function used right now. So this means the output of the first neuron is the max between 0 and its input. The output of Y2 is the max between 0 and its input. And then the final neuron output of the neural network Y is just the summation of the 2. And on the right, you can see the corresponding of these functions out there, color-coded with the same equations. So blue lines corresponds to the output of Y1, orange corresponds to the output of Y2, and then green is the corresponding of the output of the entire neural network. Now, let's say I have my property is I would like to make sure that whenever the input is between 3 to -3, I would like to make sure the output of the neural network is always greater than or equal to 1. Of course, pictorially, you can see that the green line is always greater than or equal to 1, so we know the property holds out there. But for high-dimensional neural networks, we cannot just plot the graph of the function and check the property. So we'd like to have an algorithmic way to check this property. So the nonlinearity comes because of this ReLU activation unit, which is a continuous piecewise affine function. So it has 2 modes. Whenever the input is positive, I will call the neuron is active. And whenever the input to the neuron is negative, I will call this neuron to be inactive. So since each neuron can have two phases, then we can start by coming up with a search tree that go through all possible combinations of each of the neurons being active or inactive. So when Y1 is active, this means its input have to be greater than 0. This corresponds to the domain to be on the left of that line out there. Let's take the case when Y2 is inactive. So this means that for Y2 to be inactive, X have to be less than or equal to 0 according to the equations of Y2. Now, to check whether a property hold in that particular region or not, I can solve a feasibility problem where I have the neural network is nothing but a linear function inside this region right now because I fixed the phases of all the neurons inside the neural network. So I'm interested to find an X and Y that adhere to the response of the neural network. I'm trying to find a counterexample. I'm trying to find something that violates the property. So I'm interested in Y less than or equal to 1. And I'm restricting X to be within this particular region. All the constraints are linear. If this problem is feasible, then I found a concrete counterexample that violates the property inside this region. If not, if the problem is infeasible, this means I need to go back in my tree and start traversing over this tree by flipping some of the neurons from active to inactive. Again, solve an LP, go back in my tree, flip Y1 from active to be inactive. Again, for Y2, check whether it's active or not. Whenever it's active, again, solve another LP. Some of the combinations are infeasible because both the neurons cannot be inactive at the same time. So now I covered the entire tree solving different LPs out there. So I solved in total 4 LPs. And if all the LPs are infeasible, this gives me a guarantee that the neural network satisfies these constraints. Otherwise, I found concrete counterexamples that violate them. So as you can see, this is a combinatorial problem. As the number of neurons starts to increase, this tree is going to grow, and it may take you forever just to go through all possible combinations to cover all of them. But the message is to do exact verification, sound and complete verification of a neural network, you need to enumerate all possible regions and solve feasibility problems everywhere. The other approach, which is using sound over approximation of the neural network. So given the input set, I would like to compute the red, which is the actual output set of the neural network. If it happened to be completely contained inside my PY, which is blue on the right-hand side, then my neural network is good. It satisfies the specifications, but I don't know how to compute the red region without going through all the tree branches and computing all the branches. But instead of computing this red set exactly, we can use we can relax the nonlinearity of the neural network. We can convexify the response of the neural network. And now we can use a lot of techniques of reachability analysis to propagate this input set PX through these convex green regions to get an over approximation of the output set. If I am lucky and the over approximation is inside the output constraints, then I can stop out here. Otherwise, I need to start selecting some of the neurons, split them, and which is going to reduce the over approximation error. And I can do this until I'm lucky and my over approximation is inside the set of output constraints, and I can stop out there. So in general, sound over approximation gives you some kind of doing an easy incomplete verification and scalable incomplete verification of neural networks. Most of the tools in the literature tries to combine these two ideas together, try to use some over approximation followed by some neuron splitting. Each tool comes up with its own way of doing over approximation, its own way of doing its neuron splitting. In our work, while a lot of people focus in over-approximation using convex regions, we have been focusing on using non-convex polynomials in Bernstein bases. Bernstein polynomials have a lot of very nice mathematical properties. In particular, for general polynomial in power bases, if I give you a polynomial 3x squared plus 4x plus 2, and I ask you what is the max and min of this maximum and minimum of this polynomial within a certain interval, the problem is in general NP-hard. For Bernstein polynomials, if I give you a polynomial in Bernstein bases and I ask you the same question, you look into the coefficients. The maximum coefficient is the upper bound of the polynomial. The minimum coefficient is the minimum bound of the polynomial. So you can bound and do this propagation over Bernstein polynomials very effectively. It comes with a lot of nice, even implementation-wise aspects. It can be easily parallelized over GPUs, which gives you better approximation compared to other convex region enumeration, convex approaches for over-approximation, while still giving you being computed faster than other tools. For the neuron splitting, again, I'll go quickly over the math out here. Instead of solving a feasibility problem, we instead solve an optimization problem where we add slack variables into the optimization problem, and we use these slack variables as an indicator of which of the neurons that we need to do the splitting over. So instead of going the tree from top down, and we have to traverse the tree exactly in this way, these slack variables tells us which neurons are the most problematic neurons, such that if we split over these neurons, is going to reduce the over approximation error as much as possible, which accelerates the overall process. I'm just skipping some of the details out here. And just to show you that in general, this helps the solver. So this is a cactus plot. Our tool is the blue line. You can see that our tool is able to prove more cases than other tools that existed in the literature at that time. So I hope this gives you a general sense of the why verification of neural networks is a hard problem. But we also ask the question, is all neural networks equally hard? Or can we find special structures and special semantics in neural networks that can allow us to do this verification fast? And by fast, I mean in polynomial time. And moreover, can we replace the ReLU activation unit with another nonlinearity that makes the verification faster? The answer to both questions is yes. So for ReLU neural networks, we were able to find an architecture of neural networks that we call the two-level lattice neural networks, for which the verification can be done in polynomial time in the number of neurons, still exponential time in the input dimension, and that's an unbeatable bound that that have to be always there, that you have to go to grow exponentially in the input dimension. But at least as you grow the number of neurons, the verification of these TLL neural networks will go in polynomial time. The basic idea behind these two-level lattice neural networks is this old result, which shows that any piecewise affine function and all neural networks that are using ReLU activation units are continuous piecewise affine functions. So this space of continuous piecewise affine functions can be always written as using two lattice operators, a max and a min, operating over linear functions. And by constructing neural networks that follow this lattice architecture, where you have the linear functions in the first layer, followed by a set of nonlinear ReLU layers that corresponds to these lattice operations, we can construct these TLL neural networks, for which we can verify them much efficiently. As you can see here, again, blue is our tool. We can prove a lot of more cases compared to other tools whenever the neural network follows this TLL architecture, and we can do this like 3 or 4 orders of magnitude faster than other tools in the literature. For the other question is, can we find other activation units that is still general enough to be a universal approximator, yet we can verify them in a much easier way? And again, this Bernstein polynomials becomes very handy. Actually, Bernstein polynomials is the very first known universal approximator. So using them as an activation function inside the neural network, still you can make sure the neural network still become a universal approximator. The use of polynomials in general in neural networks is something that people have been interested in because empirically it shows a lot of better results compared with ReLU activation units. And if you have them in this Bernstein basis, you get the benefit of both of them. They are easy to verify and yet expressive enough to beat the ReLU neural networks in terms of their performance. So this is just an overview of the tools that we have for neural network verification. So we have 2 tools. One of them is sound and complete. The other one is sound but not complete, which is this over approximation. And you can combine both of them or use each one of them separately. Now we have the tools. Let's go and try to see how we can use them to start building components of our autonomy stack. So in particular, we are interested in the question of assured perception. The motivation is perception is a main component in a lot of our autonomy stack right now. We rely a lot on machine vision to detect objects of interest. But as you can see in this video, in just 1 minute of data, you see how the number of times that the neural network failed to identify objects of interest like cars and so on. And this is across a lot of different operations. Neural networks used for perception are known to fail to identify all the objects of interest at all times. And this was one of the leading causes of the fatality that happened in Arizona a few years back. So by assured perception, what we are interested in is how we can design neural networks with some that do perception with some kind of provable guarantees. The problem that the motivating problem that we are going to use is the autonomous landing of aircrafts, where you have an aircraft, you have a camera. The camera is trying to detect runways. Then you have a neural network that processes the images of this camera to detect runways and produce control actions to autonomously land the aircraft.
Incredible.
So to formalize the problem, here I have my camera. I assume the states of the aircraft are the states of the camera. So I have, for simplicity, I have 4 states, which are X, Y, Z, and 1 angle. And we can generalize the results to all different 3 angles. Here I'm just going to show only 1 angle theta. Now, the camera gets you images, and I'm going to assume we have a monochromatic camera. So the images we are getting is just 0s and 1s. We don't have an RGB camera for now. The images you get from the camera can be composed into 2 parts: the image of the runway or the object of interest, and all other objects that are outside the object of interest, which is the runway. I would like to design a neural network that can classify the runway, make sure that it can always classify the runway and get rid of everything else that is not a runway. And then from the classified or detected runway, I would like the neural network to estimate the state of the camera, which is the state of the aircraft, with the guarantee that the estimated output of the neural network is always within a user-defined epsilon error. So the user would like to give me an epsilon that which is the allowable error estimation error. I would like to design a neural network that is capable of estimating the state of the aircraft up to this epsilon. The idea is we go back into how images are being formed inside the camera. So we go into the physical models of cameras. Here is an example of what's called the pinhole model of a camera, which tells you points in the 3D global view, how they are projected into the thin film inside the camera. These are highly nonlinear equations. And our contribution is to take these equations and wrap them into a neural network that have two parts. The first part is trainable parameters that corresponds to the physical parameters of the camera, like the focal length, the dimensions of the films, the dimensions of the pixels inside the camera, and so on. And the remaining part of this neural network is non-trainable. We are going to select it by hand. That corresponds to the geometry of the object that you are interested in. So you will give me a file that describes the geometry of the objects that you are interested in. And based on this geometry, I'm going to define these non-trainable parameters of the neural network. Let me show you here an example. So we constructed this neural network for runway, for example. And here is the outputs that is generated by this neural network. So you think of this neural network as a generative model that can generate images for you, depending on the different states of the camera. You can query this generative model that is based on the geometry and the physics of the camera. You can query this generative model to ask the question, if the aircraft was at this position, what is the expected view of the runway would look like? If the camera was in this position, what is the image of the runway will look like, and so on. Now, we would like to use this generative model to start designing these certified detectors and certified state estimators. The idea basically is as follows. I'm going to partition the state space of positions and angles into hypercubes. And for each of these partitions, this is going to be a set of inputs, a set of positions and angles. I'm going to propagate them using this over-approximation that I talked about in the previous slides, to compute an over-approximation of all the images that can be produced by the camera if the camera was inside this set. So I will take first set, produce all possible images of a runway that may be produced inside this set. I'll take another partition of the state space and produce all the possible images that may have been produced if I am here, there, and so on. I will use these over-approximated output sets to construct my neural network filter and estimator. I will not go through the details, but you can think of it as some kind of a matching filter. Every time I see an image collected from my camera, I would like to match it with this over-approximated set of images, and I'm asking the question whether the image I collected right now belongs to the set of all possible images that can be produced from a partition of the state space. The good news is this matching process can be encoded itself as a neural network, as a real neural network with pre-specified training parameters that we are going to select based on the geometrical model, the generative model that I told you about. And the good news is that this matching you can come up with some kind of guarantees in terms of the error that you will get because of this matching process that I talked about out here. So the result goes as follows. Let's assume that all the other objects in the scene, none of them corresponds to a runway, which means I have only one runway inside my image. I don't have two runways inside the image. And assuming that there is no noise around the runway, we don't have other objects that are close enough to the runway. This is because of how we are doing this matching process. If under these two assumptions, I can guarantee that the neural network, when it is doing this matching, will be able to identify the runway, and the estimation error will be bounded by the errors I'm getting out of this over approximation process out here, which corresponds to this Lipschitz constant of the neural network. Here is an example where here we are trying to detect this simple runway, which is just these two lines on the floor out there. On the left, you can see the output of the camera. On the right, you can see the output of our neural network after filtering out everything except for this runway as well as the error. The neural network was designed to make sure that the estimation error always be lower than or equal to half. And you can see that this is the case across the entire video. So this is just very first steps that we just started like last year or a year and a half of how to use these tools that allow us to reason about neural networks to come up with some kind of assured perception neural networks. We are still not there yet, where we hope to do things that are more general. We can be more robust to the definition of the geometric objects and so on. But as I said, this is the very first step of trying to use these tools to come up with neural networks that with some kind of assurances. Now, let me briefly go through how we can use these tools of formal verification to design neural networks with some feedback controllers with some kind of assurances. The setup is as follows. You have a dynamical system. The dynamical system consists of two parts. The first part, which is F, which is the nominal model of the system, which is assumed to be a black box. For example, you can think of having access to a simulator. Then the other part is G, which is an unknown model error, which is assumed to be a Gaussian process. The objective is we'd like to train a neural network. There is a state feedback, which takes X as an input, provide control signal U as an output. And I would like to make sure this neural network is going to satisfy some safety and liveness properties. For those who are familiar with linear temporal logic, we can design these neural networks for any bounded horizon linear temporal logic. For those who are not familiar, this is just an example of reach-avoid specification written in linear temporal logic. The tricky part is the following. I would like to train this neural network without knowing the location of the obstacles, without knowing the linear temporal logic specification, without knowing the model error G. All of this information is not available during training, yet I would like to make sure that once this information becomes available at real time, I would like to make sure that the neural network will generalize for any combination of obstacles, temporal logic specifications, and model error. The idea is as follows. We are going to train a library of neural networks, and each of these neural networks inside my library comes up with a certain guarantee. And I told you in the beginning of these slides how we can come up with some guarantees of neural networks. So each of these neural networks is going to come up with some certain kind of a guarantee. And I would like to make sure that these guarantees are composable. I can compose different neural networks at real time. And I will do all this work offline using whatever available information to me in the offline phase. Online, once I know the obstacles, once I know the temporal logic specification and the model error, I'm going to compose these neural networks to guarantee that I have a feedback controller that is going to work generalized for this mission. So each neural network individual needs to be provably correct. And the way I'm doing this compositionality, I need to make sure it is also provably correct. I'm running out of time, so I'm going to skip the details of how to do it. The basic idea is when we are training the neural network, we need to come up with some kind of a projection to ensure the neural network fits within the property we're interested in. But the good news is as follows. So given a specification phi, which is a linear temporal logic specification that I will only know at real time, and my algorithm is going to give you this composition, which is how to compose all the neural networks together. The probability of satisfying this LTL specification that you came up at real time, not during the training time of the neural network, is close enough to the optimal continuous piecewise affine controller that exists out there. And remember, real neural networks are nothing but just a continuous piecewise affine functions. So I can bound the error between the probability of satisfying the specification minus the best possible neural network that may exist out there. And the bound that on the right-hand side depends on some of the design parameters we use to design for example, the number of neural networks inside your library appears inside this delta out here. So as you have more and more neural networks inside that you trained inside your library, this error is going to get smaller, but you need to train more neural networks. The smaller the number of neural networks you have in your library, this error is going to get bigger. Here is an example. So, so this paper by Dorsa Sadiq's group at Stanford showed the following. So for meta reinforcement learning literature, if you are trying to train a neural network, then you try to adapt it to change its behavior to generalize to different environments. They showed that these four workspaces out here, the trajectories belong to different homotopy classes, and it is impossible to transfer the behavior of the neural network using stochastic gradient descent. It is impossible to change the behavior of the neural network across these different homotopy classes. So on the bottom, we show you the result of one of the tools for meta reinforcement learning out there. And as you can see, for the workspace for which the neural network was trained on, for all different combinations of the locations of the obstacles, the neural network can generalize very well out there, but cannot generalize for workspaces that belongs to other homotopy classes. While in our case, because we are not adapting the neural network using continuous gradient descent, we are composing different neural networks which allow us to some discrete jump in the behavior of the neural networks. We can guarantee that we can generalize to any different combination over all these different homotopy classes out there, as given by the theorem that I showed you. Here is another example where the neural networks were trained for a certain environment, and then my student will jump on, change the environment. Now we can recompose at runtime. We can recompose the neural networks that we have at runtime to adapt to changes in our temporal logic specification or to adapt to different changes in the obstacles. Here is, let's put everything together. Let's let's try to make sure we have systems that are safe. So instead of trying to verify or to design the entire neural network to be safe, let's try to come up with a shield. If you are from the reinforcement learning literature, it's called a shield. From the formal verification literature called root of trust. From the control theory literature called the control barrier function. So we'd like to design a neural network that will take control signals generated by your controller, project them to the closest possible safe action, and use the closest possible safe action to activate the actual system. So if your controller provided safe actions, then it will just pass through this verified neural network. If the control actions generated by your neural network, by unverified neural network, happen to be unsafe, this neural network, the control barrier function or the shield, whatever you, or the safety filter, is going to project it to the closest possible safe control action. Now, we are going to design this one, verify it, make sure it gives the safety guarantees. Here is the result, where we have a neural network that is actually terribly trained, that is trying to hit the obstacles instead of avoiding them. But once we put the safety shield, you will see that we can always make the system safe. As I said, the unverified neural network is terribly trained, but then the safety shield can always kick in and make sure that the entire system is safe. And here are other results showing that using these verified neural networks during the training of the unverified neural network helps with conversions, helps with making sure the entire system is safe, and so on. I'm running out of time, so I'm just trying to wrap up out here to leave some time for questions. So I started by showing these articles about neural networks fail in real-life settings. And I hope that I convinced you that formal verification of neural networks have some hope of solving part of the problem. It may not be able to solve the entirety of the problem, but it can be a useful tool that can help us designing better neural networks with some kind of assurances, both in terms of their estimation errors and their generalization for different environments. With this, I would like to stop here. Thank all my students and postdocs. I just presented their work, and thank our sponsors for supporting this research. And I would like to hear more your questions. Thank you very much.
Thank you for the very interesting talk. In terms of questions, feel free to unmute yourself and ask questions directly, or feel free to write them in the chat. Then I will read them for you. Is there anyone that would like to go first? Right. If not, or was there someone unmuting themselves and I cut in?
Yeah, Mark,
please,
if I may.
Please, Emilio.
Yeah,
of course.
In the dark.
Right.
So, what seems difficult to me is, so if you know what are the correct outcomes or the incorrect, counterexamples or something like that, isn't that what is hard to do with standard methods? And that's why we want the neural networks. So in a sense, doesn't specifying those counterexamples with linear constraints and things like that defeat the purpose of the neural networks in the first place?
Yeah, that's a very interesting question. So, of course, sometimes coming up with the specification itself can be extremely hard. How can I come up with these linear constraints to define that a neural network should identify cats as cats? What is the linear constraints that specify what a cat is, for example? So for the individual neural network itself, Yes, it is sometimes it is hard to come up with these constraints. And this is why a lot of our work focus on coming up with this specification for the entire system. So, for example, if I give you the dynamics of your vehicle and some neural network that is your state feedback controller, this PX and PY right now becomes specifications on the behavior of the trajectories of the overall system, which is in this case, I would like to make sure I don't hit the obstacles, which means your X have to be outside a certain convex set which corresponds to the obstacles. So levitating this to the system level makes the specification more understandable and easier to come up with. If you think of your dynamics itself, if it was a neural network, then now you can take these two neural networks together, compose them together, and now you have this PX and PY on the trajectories of your closed loop system. But I completely agree. Yeah, sometimes coming up with this, even with linear temporal logic, you know that sometimes coming up with the specifications of LTL itself can be as hard as solving the problem. But we try to find a set of, and this is why I said formal verification may help solving some of the problems, but not all of the problems, and that's big part of it. The specification itself is a challenging part. For the autonomous landing one, it was easy for us to come up with the specifications because the system is contained. It is not like a ground vehicle running in the streets with pedestrians around you and so on. The system is well defined and is not changing over time. For open systems like ground vehicles with a lot of people around you and so on, I completely agree. This may not be the right tool to solve the problem. Does this answer your question?
Yeah, I mean, I didn't want to imply that this was not the right tool to solve the problem. I mean, this is not the intent.
For open. So what I'm saying is for problems that contained problems. Think of closed systems where there is not a lot of other objects moving. You can try to specify them, but for example, how to specify the behavior of humans running around a ground vehicle. Yeah, these kind of behaviors, the specification is hard. And if you don't have a formal specification, you cannot use formal verification in general.
If you go back, I think that was one of your last slides, maybe just one slide before another one. Oh, no, was the one with just go back. So where you had the network, okay, this one.
Yes.
Okay, so I kind of like agree with the overall structure here, right? But this safe by design root of trust network, why does it have to be a neural network? Is something that we kind of don't understand. So in a sense, why don't you use those counter examples, those like a specification that are a little bit more straightforward to analyze, for your safe by design architecture?
So the motivation here is this unverified network is extremely complex and is doing a lot of things like trying to detect stop signs and pedestrians, and as we saw that the problem is combinatorial. So coming even with counterexamples for this unverified network can be extremely hard and challenging. But let's add another simpler sensor, which is in this case is LiDARs, and use the specification out here is just not to hit obstacles. Which you can get this information from LiDAR. So this root of trust out here will not make you stop in the stop sign, for example, or when the traffic light turns red. It will just try to make sure that you don't hit other obstacles around you. So it is hard to find counterexamples for the original neural network, but this is a simpler setup where you can come up with these specifications, and the neural network that is needed out here is going to be smaller. So this is why we can verify the properties of this neural network, that the output that you will get out. So we'll train it, we'll try to find the counterexamples for the green one, not for the yellow one. You'll find the counterexamples for the green one, use them, repair the neural network until you guarantee that this green one satisfies its own specification, and then put them on top of each other.
Okay. Thank you. Yeah, I don't want to take all of the time. So if other people want to ask questions.
Right. Otherwise, I just wanted to ask a quick clarification. If you could also represent sequential tasks in your framework.
So you mean, for example, this framework out here, your specification can be a bounded horizon linear temporal logic specification, which allows you to reason about sequential tasks, if I understand the question correctly. So it can be go to this one, followed by doing this, and then
exactly.
Right. Yeah. And we can generalize. The framework is for bounded horizon linear temporal logic. So the H you see on the right-hand side of the bound out here is the horizon of the temporal logic specification. The longer the horizon, this error will grow because of how the probabilities gets multiplied and so on.
All right, thank you. All right, there is a question in the chat. Let me share it. It says, thank you, Professor, for your sharing. It seems in the video you shared that the car using a shield to help avoid pedestrians appeared somewhat jittery. Would this be an issue, or it's just due to some settings in that scenario? Would this be a common phenomenon in similar systems?
So the jittering is because the actual unverified neural network, we try to have a terrible one. Okay, and we wanted to make sure it is safe, even if you have a very terrible. So actually the unverified neural network is always trying to take us to the center of the street, while the shield is always trying to get us outside the center of the shield, and this is why you see this jittering going back and forth. But what we showed out here, and in this video, both of them were trained separately. We trained the unverified network by itself, and then we trained the safety filter, and then we just composed them. The remaining part of the results we have out there is when you train the unverified neural network with the filter out there, and you will see an improvement that is happening out there, because now the unverified network is aligning itself with the behavior of the filter and takes this as part of the black box dynamics that is used for training. So there were training using reinforcement learning, for example. So you will get better when you use it during training. If they are separate, if each one of them is trained separately, then expect this kind of jitter to happen.
Right, thank you. If it answers the question, or if there's any follow-up, please let us know in the chat. Yeah, I think this answered the question. I also wanted to follow up on maybe a last question from my side, and I thought it was very interesting on the two-level lattice architectures that you said, the TLLs, which were verifiable in polynomial time. What I was wondering here is, do these architectures have the same expressibility or same performance in solving problems as other architectures? So what I'm wondering is, if you were to use TLLs to solve perception, do they perform just as well as other architectures?
So theoretically, they are as expressive as any other neural network, because any neural network can be written in the TLL form.
Right.
Okay. Because this is a general form for the space of CPWE functions. In reality, in practice, what we have noticed is training them takes more time than training just like a feed-forward neural network. It takes more and more epochs to make sure to train it to get to the same exact performance. What we are doing right now is we are doing a compiler from feed-forward neural network into the TLL form. So you'll train your neural network in whatever form you are interested in, and you are going to take it to transform it into the equivalent TLL form and verify it out there.
Right. I think this leads to a follow-up question that I wanted to ask on this is sort of what you think are sort of the next big challenges that you want to work on for this to come to fruition, and maybe if you see this already being mature enough to being applied in practice and that you would trust, or which other challenges you see on the horizon before that would happen.
So we're very excited about this result of using other activation units, because what is the reason of using ReLU activation units? What is the scientific reason behind using ReLU activation units? There is not they are easy to use. GPUs know how to handle them, and they are universal approximators, but there are a lot of other universal approximators out there. And the expressivity of CPWA functions compared with other functions is actually limited. Polynomials are more expressive. So with this new paper out there, we showed that we trained the ReLU activation function, ReLU neural network, and the Bernstein neural network. The Bernstein neural network, in terms of performance, was much better than the ReLU neural network. This is not surprising. There is a whole literature about what is called as SPI neural networks or polynomial neural networks that people have shown to be more expressive and better in doing a lot of very challenging tasks compared to ReLU activation units with more compact neural networks. Typically, the problem out there was when you are training polynomial neural networks, you fall into what is called gradient explosion. If your activation function is x cubed, when you do the back propagation, you'll get 3x squared. And if x is greater than 1, the gradient is going to explode. And we have mathematical proofs out there that this is not going to happen in this particular neural network. The gradients are always bounded by the coefficients of the polynomial. So this is an exciting direction for us. If you look into the table out here, I'm just showing you when you do this this over approximation of the neural network, just to see the difference in the errors you get out there. Let's take the first column, for example, and last row. If you use ReLU activation units, the error in the over approximation is this very scary number. While using Bernstein polynomials, the over approximation error is this -12 number. So you see that doing this inexact verification becomes much easier and much faster with these new architectures out there. And I'm pretty sure people will come up with more and more architectures that makes this verification easier, because this bounding is an essential step in what is called assured training, where during training you can use this as an upper bound over the error in satisfying certain properties. And you use this as a regularizer during training. We use it, for example, to train certifiably fair neural networks. Others are using it to train certifiably robust neural networks, and so on. So I think this direction of coming up with new architectures of neural networks that fits our applications from perceptions and control is something of interest, and as well as trying to see where is the limit where we can use these neural networks in practice.
Right, thank you. This was very helpful and insightful, just as was the talk. And I think if there are no last questions, in that case, I think we will thank you, Yasser, one more time for the great talk. And I wish you a great day, and see everyone else back for the next Autonomy Talk.
Thank you very
Bye,
much.
everyone.
Appreciate it. Bye.